Something changed while the world was not looking. After 8 days tucked behind the sun, 3i Atlas stepped back into view and immediately defied the script we teach in classroom comet physics. It brightened too fast, its colour skewed in ways that should not happen for dust and ice. If jets did the pushing, the sky should be full of the missing debris. Telescopes see motion that hints at a push without a pusher. This is a real-time mystery with measurable stakes. Stay with us through the next hour. Like and subscribe now so you do not miss the next piece of evidence. The first frames arrive with the kind of electricity that makes sleep impossible. Halloween skies deliver a faint, stubborn smear rising over the northeastern horizon, and then within hours, that smear behaves like anything but a routine comet. 3i Atlas had just survived the glare of solar conjunction, the period when the sun hides an object from earthly eyes. We expect a slow return to normal tracking, careful photometry, and the kind of patient science that unfolds over weeks. Instead, we get questions loud enough to rattle the telescope dome. What does normal look like for a visitor from another star? You picture a dirty snowball. Water ice boils under sunlight, gas escapes, dust follows, and the gentle thrust from those jets nudges the nucleus so slightly that only specialists care. The coma grows. The tail flows away from the Sunday brightness, rises as distance falls. It is predictable enough that textbooks use it as a comforting example of physics working as advertised. 3i Atlas looks back at that playbook and shrugs. Observers report a rapid surge in brightness near perihelion, the moment of closest approach to the Sunday. A surge is not unusual by itself. The surprise is the pace and the colour shift that followed. Parts of the spectrum went bluer than the solar reference, a bizarre signal for what is supposed to be gritty, dark dust warmed by sunlight. Think about what must happen inside an object to flip that switch so quickly. If a cap of fresh ice broke open, if fragments flew, the solar system should be glittering with the wreckage. That leads to a hard number. To explain the measured change using ordinary jets, the object would need to blow off a significant share of its mass. Translate that into plain terms, and you get billions of tons of gas and grit. A cloud that large is not subtle. It reflects sunlight. It scatters radiation. It leaves fingerprints up and down the spectrum. Yet in the first hours after the surge, searches come up short. The debris field does not present itself on cue. Meanwhile, position measurements introduce a second thread that will not let go. Several instruments agree that the sky location is a little off from where pure gravity would put it. General relativity tells us that the sun bends light, solar radiation pressure pushes dust. Both effects are real and measurable. Subtract those and a small residual remains, as if something gave 3i Atlas an extra nudge. In other comets, the explanation would be simple. Outgassing did it. Here, that answer loops back to the missing cloud problem. This is where the story shifts from a curiosity to a testable paradox. Either the debris exists and our instruments will catch it as the geometry improves, or the debris does not exist at the required scale and we need another mechanism. That mechanism could be mundane yet underappreciated. It could be structural, it could be chemical, it could be a kind of jet we have not modelled because the surface is not what we think it is. Each option carries predictions we can check in the coming weeks. The context matters. 3i Atlas is only the third confirmed interstellar object, and it does not owe us familiarity. We have a tiny sample size and a bad habit of forcing the strange to fit the familiar. Still, nature has a rhythm. When one measurement strains the model, you adjust parameters. When several, the measurements point in the same uncomfortable direction, you start writing proposals for extra telescope time. That is what is happening now. The phone lines between observatories are busy. In the next parts, we will pull the puzzle pieces into a sharper picture. We will look at the surface that may be a mask carved by cosmic radiation. We will examine chemistry that reads like it came from somewhere else. We will follow light that refuses to scatter like normal dust and an orbit that seems a little too choreographed for comfort. For now, hold on to the paradox that started it all. A comet that brightened too fast, changed colour in a way it should not, and moved as if pushed by a hand we cannot yet see. Start with a simple thought. What if the face we are staring at is not the original face at all? Imagine a wanderer coasting between stars for 3 to 11 billion years, while invisible bullets of cosmic radiation chip and rebuild its skin. Layer after layer of carbon-rich, Material forms and reforms until a crust 15 to 20 meters deep seals the interior like a dark varnish. By the time 3i Atlas drifts into our daylight, we are not seeing the birthplace. We are seeing the travel scars. Cosmic rays are not gentle. They split water into hydrogen and oxygen. They shuffle carbon chemistry so that carbon monoxide becomes carbon dioxide, then back again, then onward to complex organics that redden reflected light, over eons that chemistry cycles like a tide. Bond, break, rearrange, repeat. The result is a skin that behaves like an insulator and a filter. It changes which gases escape first and how light scatters off the dust. That skin does more than paint the color. It edits the story we think we are reading. When we point a spectrograph at the coma, we expect a window into the interior. Instead, we may be sampling the aftermath of radiation processing. The shell limits heat flow from the sun into the core, so sublimation can occur along hidden channels and fractures rather than evenly across the surface. Jets might burst from small vents while most of the crust stays intact. That would explain a comet that seems active without presenting the obvious snowfall of fresh debris. The crust also slows time from a thermal point of view. Organic material is a poor conductor compared with clean ice. A thick blanket forces heat to move by tortuous paths, which delays and distorts the response to sunlight. That means bursts can arrive late, clustered, and directional. In a textbook comet, the brightest moments map neatly to solar distance. In this case, the clock is wrong because the thermometer sits behind a wall. Laboratories can test parts of this idea. Take mixtures of ices and simple organics. Expose them to simulated cosmic rays for long runs. Measure changes in color, polarization, and gas release. Teams are doing exactly that. If they reproduce the strange red slopes and the exotic polarization while building a fragile, insulating residue, then the crust hypothesis earns weight. If not, we go hunting for a different kind of dust or a different kind of process. There is a second consequence that matters for the missing cloud problem. If the skin is strong enough to channel gases into narrow vents, then jets can push with surprising efficiency while throwing off far less visible material than a broad surface blowout would. Thrust without fireworks is not magic. It is plumbing. A nozzle accelerates flow. A choke point selects particle sizes. The sky could stay cleaner than our intuition expects, even while the nucleus gets nudged. Post-perihelion geometry helps us look beneath the mask. As 3i Atlas moves away from the sun, deeper layers warm and begin to vent. Each new molecule that escapes carries a tag from its birthplace inside the body. Water should appear from below if it exists in quantity. If it does not, the spectrum will continue to shout carbon dioxide and carbon monoxide, with only a whisper of hydrogen from dissociated water. That ratio tells us whether the interior matches the surface or whether the crust is a special case. There is also a mechanical clue. An ancient shell should be crazed with microcracks and voids. Rotation can pump those cracks like bellows. If jets rise and fall with the spin period, rather than with solar distance alone, the surface is dictating the show. High cadence photometry can catch that pattern. It is a fingerprint of plumbing rather than a simple heat lamp. All of this reframes the mission. We are not only asking what this object is. We are asking what billions of years in deep space do to anything that dares to travel that long. The crust hypothesis solves the red color, the carbon dioxide dominance, and the stubborn survival of a skin that should have burned off if it were thin. It leaves open the metals puzzle and the choreographed path. It narrows the set of places where answers can hide. The next weeks are a chance to separate mask from face. Look for delayed outgassing that tracks rotation instead of distance. Look for the hydrogen halo that marks real water, or its absence if water is scarce. Look for dust grains whose polarization matches radiation lab products. If those signals line up, the mask theory stands, and we can read the diary of a journey across the galaxy. If they do not, the story turns again, and we go deeper. Begin with the recipe everyone memorizes. A comet is mostly water ice laced with dust and a handful of simple gases. Now, erase that page. Spectra from 3i Atlas announce a composition that flips the ratios. Carbon dioxide dominates by a factor around 7-1 compared with water, with carbon monoxide riding unusually high as well. The reflected light runs red, a sign of complex organics painted across the surface. If you were expecting the familiar signature of a cold snowball, you are holding the wrong checklist. The red slope alone would not be a crisis. Radiation can redden surfaces and build tar-like residues from simple carbon chemistry. What jolts the conversation is the combined picture. Carbon dioxide outshines water. Carbon monoxide refuses to sit quietly at trace levels. The waterline, the usual anchor for comet activity, is faint enough to make observers squint. When a single number looks odd, you look for error bars. When the entire pattern leans the same way, you start asking what kind of nursery could raise an object like this. Then, the metals step onto the stage. Emission lines in the gas plume point to a nickel-to-iron balance that echoes engineered alloys rather than cosmic dust averages. Nickel relative to cyanide rises far above the catalogue of familiar comets, including the previous interstellar visitor Borisov. No one likes to accuse nature of cheating, yet the odds of matching industrial-like mixtures by accident come out painfully low in several analyses. The phrase less than 1% is not a verdict, but it is enough to keep a research group awake. There are natural ways to push nickel and iron out of their usual handshake. Supernovae do not explode politely. Different layers forge different elements, and fragments from those layers can seed future objects with eccentric ratios. A birth cloud rich in such ejecta might produce a body that carries a metallic accent the way a region can carry a dialect. If 3I Atlas formed in a pocket polluted by a particular stellar death, the plume chemistry could be a fossil of that event. Another candidate sits closer to home, if home means the skin we described earlier. A crust sculpted by cosmic rays for billions of years could trap or preferentially release certain species, making the coma look stranger than the interior really is. If gas escapes through narrow vents, it may fractionate on the way out. Heavy molecules linger, light ones escape. The result is a jet that speaks with an accent imposed by plumbing rather than by birth. Before anyone hangs a final answer on a single spectrum, cross-checks have to do their work. Instruments on different platforms see the same lines. Calibrations are audited. Backgrounds are subtracted and then subtracted again. The numbers keep settling near the same surprising place. Carbon dioxide strong, carbon monoxide elevated, water shy. Nickel standing taller than iron would suggest, if you assumed normal solar neighborhood dust. This chemistry matters for dynamics too. If water is scarce, then the familiar water-driven jets cannot be the whole story for thrust. Carbon dioxide and carbon monoxide sublimate at different temperatures and depths. They can power activity at distances where water would sleep. A body fueled by those gases might wake earlier, surge faster, and change character as deeper reservoirs switch on. The timing of the perihelion brightening begins to make a different kind of sense, even as the missing debris keeps the paradox alive. There is also a quiet clue in the way the color changes with time. A surface dominated by radiation-processed organics should not only be red. Under intense heating, it can crack, vent, and briefly expose fresher material that scatters light differently. That would tug the spectrum toward the blue in specific bands, matching a fraction of what the solar observatories recorded. It is not a full explanation. It is a breadcrumb that points toward coupled chemistry and structure. If composition is the map, we are still arguing about the projection. One path says, rare birthplace enriched by violent stellar history. Another says, ordinary birthplace, extraordinary weathering during a billion-year voyage. A third whispers about selection effects and small number statistics. We have exactly a handful of interstellar visitors to compare, and chance can masquerade as pattern when the sample is tiny. The only cure for that is more data now and more objects later. For this object, the next steps are direct. Track how gas production rates evolve day by day. Watch whether water rises from deeper layers as geometry improves. Measure nickel and iron again, with different instruments and longer integrations. If water refuses to show and metals hold their odd balance, then composition alone demands we keep the cameras rolling. Even before we tackle light that misbehaves and an orbit that looks suspiciously tidy, the chemistry writes a headline. 3I Atlas does not taste like any comet we know. Light from the sun carries a subtle fingerprint. When it bounces off a fog of dust around a comet, the electric field lines prefer certain directions, and that preference is what polarimetry measures. In ordinary comets, the pattern is gentle and familiar. As the viewing angle changes, The signal slides from slightly negative to slightly positive and back again, with amplitudes that sit comfortably inside decades of catalogues. 3i Atlas refuses to sit anywhere near those boundaries. The negative, polarization plunges far deeper than anyone expects, and it stays stubborn when the angle says it should relax. The first instinct is to blame particle size. Micron-scale grains scatter light differently than fluffy clumps or compact shards, and a swarm full of tiny fragments can drive the signal downward. But the numbers do not cooperate. To reach the observed depths, you need either an extreme abundance of submicron grains or an exotic internal structure that channels light in a coordinated way. Radiation-processed organics can build exactly that kind of structure. Imagine soot, like networks with voids and filaments and delicate bridges. Add years beyond counting under cosmic ray bombardment, and the mesh becomes even stranger. There is a second lever that polarimetry pulls. Shape and orientation matter. If grains are elongated, or have plate-like features, and if they become aligned even weakly, the scattered light can swing hard. Electric charging in the coma, magnetic fields, carried by the solar wind, and aerodynamic drag in jets can all nudge grains into partial alignment. Most comets show only hints of this effect. 3i Atlas looks like an exception. The pattern across the coma is not random fuzz. Observers see gradients that track jets and arcs rather than a uniform halo. Laboratories are racing to catch up. Groups place analog ices and organics in cold vacuum chambers, bathe them in simulated cosmic rays, and then measure how the residue scatters and polarizes light. Early results show stronger negative dips than pristine dust can make, especially when the residue is porous and layered. That is progress, yet the lab curves still fall short of the most extreme measurements from this object. Reaching those depths may require aggregates with hierarchy on several scales at once, from tens of nanometers up to many microns, a kind of fractal sponge that nature rarely assembles in one piece. There is also the curious dance between color and polarization. The surface reads red under gentle heating, which suits an organic veneer. During the perihelion surge, the spectrum briefly swings bluer in narrow bands. If fresh fragments burst from cracks inside the crust, the youngest grains can scatter light, more like glassy ice, and less like tar, tipping the color, while polarimetry remains ruled by the dominant porous population. That mixed signal would look exactly like what the solar observatories recorded, a fast blue nudge riding on top of a deeper, stubborn polarization trough. Geometric tests can slice this knot. Map polarization as a function of distance from the nucleus, and watch how it evolves with rotation. If the deepest negative values travel with a specific jet, then alignment and grain birth conditions are steering the effect. If the trough spans the entire coma and hardly changes with spin, then the grain population is globally unusual. Multiband measurements add a further filter. A trough that weakens rapidly toward longer wavelengths points to very small particles. A trough that holds steady suggests complex shape and internal voids doing the work. There is a more exotic possibility that researchers raise carefully. Coherent backscattering in extremely porous materials can amplify negative polarization beyond what single scattering models permit. Picture photons entering a maze of tunnels and returning along nearly the same path, interfering with themselves in a way that favors certain directions of the electric field. The effect is well known in powders and snow at very small angles. To dominate at the larger angles reported here would require a maze, far stranger than typical comet dust provides. If the radiation crust is the architect, then the story stays natural yet remarkable. Eons of processing turn the skin into a factory for delicate aggregates and microplatelets. Vents carry that material into space with gentle charging and shaping forces that tilt grains as they leave. The coma becomes a laboratory in which light reveals the microphysics of alien soot. If the lab cannot reproduce the trough, even with heroic effort, the field will be forced to search for a missing ingredient in the environment. Perhaps the grains are born under pressure, pulses that weld them into lattices. Perhaps electric fields near the nucleus are stronger than models allow. Either way, the misbehavior of light is not a sideshow. It is a central clue that touches composition, structure, and activity all at once. It tells us that the dust is not ordinary, that the surface is not passive, and that the jets are more than simple steam vents. With this in mind, the next puzzle lands with extra weight. A path through the solar system that looks suspiciously tidy, as if someone threaded a needle while our cameras were blinking. That is where we go next. From a distance, the path looks accidental. Up close, it reads like a thread pulled through a set of moving needles. 3i Atlas does not just dive in and slingshot out. It slices the solar system on a retrograde track, crosses the plane where the planets live within a handful of degrees, and times its closest sweep past the sun during a window that leaves Earth squinting through glare. Chance can do this once. The feeling of choreography comes from how many once events arrive together. Start with retrograde motion. Most planets and most long-lived debris circle the sun in the same direction as the original disk. A visitor from interstellar space owes us no allegiance, yet a backward path still matters. It raises encounter speeds, and it alters how dust and gas are stripped by sunlight and wind. Now add the plane problem. The closer an orbit lies to the ecliptic plane, the richer the menu of planetary flybys. 3i Atlas rides within roughly 5 degrees of that plane, while coming from the wrong way round. Dynamically speaking, that is an invitation to meet everyone at once. Where you cross matters as much as how you tilt. Lines of nodes are the 2 points where an inclined path cuts the planetary plane. Place those crossings near the longitudes of Mars or Venus or Jupiter, and you raise the odds of a close pass by tens of millions of kilometers. Push the crossings a little, and the parade evaporates. The object we are following managed to thread several opportunities in a single season. Each pass looks ordinary on its own. Stack them, and the calendar begins to look engineered. Timing is its own character. The moment of closest approach to the sun landed during an alignment that kept Earth mostly blind. Solar conjunction is not a conspiracy. It is geometry. Still, the effect is practical. The best hours for fast change arrived when optical telescopes on the ground could not watch continuously. Spacecraft with solar coronagraphs saw the surge, yet the ideal follow-up from Earth had to wait. When we say the trajectory looks choreographed, this is part of what we mean. The beats hit when our main stage was dark. Statisticians will raise a friendly flag here. It is easy to compute a tiny combined probability after the fact. A better question asks, how often random hyperbolic visitors would land in similar alignments if you watched long enough? Selection effects also bite. Surveys spend a lot of time near the ecliptic because that is where most small bodies live, so we are biased toward interstellar paths that cross that lane. A tidy orbit might be favored in the catching, not in the launching. The counterpoint is retrograde entry, plus a near-planar cut, plus clustered flybys, plus a blind perihelion. Each term has its own penalty. Even with bias, the stack is heavy. Dynamics gives us tools to separate narrative from necessity. Integrate a cloud of trial orbits that share the measured inbound speed and direction, then let the solar system tug on them. Small changes in the approach vector swing the line of nodes and move the encounters around the clock. If the observed track sits on a narrow ridge of solutions, then the path is a rare throw of cosmic dice. If many nearby paths also collect multiple flybys while skirting Earth's view, then what feels like choreography is simply a well-used gravitational corridor. Non-gravitational nudges complicate the picture. A jet that fires near perihelion can twist the path by a whisper, and that whisper can shift future encounters by large distances. In a prograde case, the same jet might matter less. On a retrograde near planar track, the leverage grows. This is one reason the missing debris cloud matters so much. A strong jet without fallout would be an efficient steering mechanism with little evidence left behind. A strong jet with a visible tail of rubble would be a standard Comet story with a lucky calendar. There is a quieter possibility that belongs on the table. The galaxy does not send visitors at random angles forever. Over long times, the gravitational field of the disk and the way we search can sculpt the set of paths we notice. If the true distribution favors shallow cuts through the planetary plane, then 3i Atlas is not alone in that preference. What remains hard to absorb is the synchronized schedule. The object skimmed within striking distance of multiple planets and showcased its wildest behavior while the largest audience was blocked. Observers will not settle for vibes. High-precision astrometry around the December approach will lock the hyperbolic elements to many more decimal places. Radar, if it bites, will refine the velocity and distance during the pass to a level that forces the models to behave. With those numbers in hand, teams can rewind and replay the entry a million times and rank how outlandish the real path is compared with its neighborhood. Either the choreography dissolves into a common step, or it stands as an outlier that refuses to fade. All of this turns the next act into more than spectacle. The blue surge at perihelion is no longer just a dramatic light show. It is the moment when any steering by jets should announce itself in the sky. If the cloud appears at the scale the thrust would require, we tuck the path under natural mechanics with rare but credible timing. If the sky stays cleaner than that calculation allows, the question of choreography sharpens rather than softens. The stage lights rise again, and the color of the flame becomes the loudest clue. Perihelion is the crucible. That is the instant when a visitor swings closest to the sun, and every volatile inside wakes up or fails to wake. In ordinary comets, brightness rises as heat turns ice to gas and dust follows along. 3I Atlas did not rise. It leapt. Light curves steepened in a rush, measured in hours rather than days, and the color nudged toward the blue in select bands. Multiple solar observatories caught the same surge, which means we are not arguing over a single instrument. The sky itself put on the show. Blue matters because it hints at energy distribution. Dust warmed by sunlight tends to redden the spectrum. To swing blue, you need either tiny fresh fragments that scatter more like glass than soot, or you need gas emissions that spike in the shorter wavelengths. Either path demands a trigger. Fresh vents that split a cap, a slab that fractures and flips, a pocket of volatile molecules that punches a jet through the crust. Each candidate carries a price in mass that we can estimate. Here is the uncomfortable arithmetic. If jets are doing the pushing implied by the position offset, then the nucleus must have lost on the order of 15% of its mass during that window. Translate that into human scale. Billions of tons of gas and dust should have flooded the near-solar environment, a cloud that large is not shy. It would scatter sunlight into a broad halo and paint ultraviolet tracers that space telescopes are built to find. It would alter polarization across the coma and leave a fingerprint in radio lines as molecules relax. Geometry bought the object some cover. The key hours unfolded with the sun as backlight and Earth looking through glare. Ground telescopes could not stare continuously. Coronagraphs saw the brightening, but they do not always capture the faintest wings of a dust field. That excuse is temporary. As the object climbed away from the sun in the following days, the viewing angle improved. If a vast swarm exists, it should drift outward, thin slowly, and remain detectable as an extended structure larger than the ordinary coma. Observers know where to look. A real debris field will not be a clean circle. It will stretch along the path and broaden into a fan with size sorting by sunlight pressure. Small grains get pushed harder and run ahead. Larger grains lag and hug the track. Spectrographs add another layer. If water dominated the mass loss, hydrogen should bloom in ultraviolet lines as sunlight breaks the molecules apart. If carbon dioxide and carbon monoxide dominated, their daughters will paint the spectrum instead. The ratios tell the tale, even if the dust is faint. There is a clever escape route that collapses if the cloud appears. The crust may act like a nozzle, channeling gas through narrow vents that accelerate flow and carry fewer large grains. Thrust per kilogram rises when the exhaust is fast and clean. In that case, the nucleus can change course without throwing a blizzard of rubble. The sky stays tidier than intuition expects because the plumbing is efficient. We would still expect to catch fine dust and gas, but not the gravel-rich spray that a broad blowout would produce. The blue swing does not let the object off the hook. Fresh surfaces make sense for small, bright fragments, yet they also tend to seed a visible trail as those fragments cool and shatter. Gas lines can glow blue, yet they march in patterns that stick out in spectra. Teams are combing those patterns now. If the surge was driven by a narrow set of molecules, signature will show. If it was driven by a shift towards submicron grains, polarization should respond with its own telltale dip. Another test sits in timing. Standard comet physics links brightness to distance from the sun with a smooth curve. A sudden jump suggests a threshold event such as a seal breaking or a cavity venting. Once the system settles, the light should relax back toward a predictable slope. If instead, the object keeps flickering with short, sharp bursts, rotation and internal plumbing are in charge. That behavior would fit a crust riddled with channels rather than a single catastrophic crack. Energy bookkeeping turns this section from spectacle to audit. The sun provides a predictable heat budget at a given distance. If the brightness gain and the measured gas production together exceed what that budget can deliver, then there is either a calibration error or a hidden pathway for energy release. Phase changes can hide energy for a while and then dump it. Structural. Stress can store energy and release it when fractures run. Both ideas are natural. Neither removes the requirement that matter must leave to provide thrust at the measured level. The next images and spectra carry a simple verdict. Find the cloud at the scale implied by a massive jet, and the story leans back toward the familiar. A rare object with an efficient engine, yes, but still a comet roaring under harsh light. Fail to find the cloud and the case grows stranger. Efficient thrust without matching fallout would force us to revisit assumptions about vent geometry, grain birth, and maybe even about low-mass ways to alter motion in a dense radiation field. The color of the flame at perihelion was blue. The next test decides whether that blue was a spotlight on standard physics or a hint that something else is on stage. Einstein gives us the first move. Mass bends space and space bends light, so a beam that skims the sun should arrive shifted by a small but measurable angle. Solar radiation pressure adds a second nudge by pushing dust away from the star. Put both together, and you can predict where a comet should appear on the sky during a close solar pass. Observers did the subtraction with care, and still found a leftover. A few arc-seconds of position do not sound like much, yet at interplanetary distances that is a shove you can feel. The clean test is to watch in several colors at once. Millimeter arrays, listen to molecules that trace the gas. Optical cameras track the photocenter of the coma, and when lucky, the glare-muted speck of the nucleus itself. Radar can measure distance and speed directly if geometry cooperates. If every channel points to the same extra nudge after you account for bending and pressure, then the effect belongs to the body and not to a trick of light. If the offset appears only in the optical center, asymmetry in the coma may be dragging the centroid away from the true path. Coma tricks have fooled us before. A jet on one, the side can flood the camera with light and pull the measured position toward the bright wing, even though the nucleus sits elsewhere. The fix is patience and cadence. Track the object across a full rotation and watch the measured center wobble. A centroid that traces a small loop with the spin is a photometric mirage. A centroid that drifts steadily in one direction while the spin turns is something else entirely. High-cadence astrometry near the December pass will make that distinction unambiguous. Suppose the residual is real. The simplest answer remains thrust from outgassing. Gas escaping through a vent acts like a rocket, and the direction of that rocket changes as the nucleus turns. Dayside heating strengthens the effect, nightside cooling weakens it, and the sum over a full spin can be a net push if the vent geometry is lopsided. Traditional water-driven jets explain this behavior well for many comets. 3I Atlas complicates the story because the chemistry hints at carbon dioxide and carbon monoxide playing a larger role, and because the sky has not yet yielded the debris field that a very strong jet would imply, there are more subtle forces on the menu. Thermal recoil can shift motion when one hemisphere re-radiates heat more efficiently than the other. Ionized gas can feel the interplanetary magnetic field, and if that coupling transfers momentum back to the nucleus through charged dust, the push can deviate from a pure radial direction. Photophoresis can shove very small grains in a gas-rich environment, altering the mass distribution in ways that tug the measured center. Each mechanism is weak on its own. In a crust with narrow vents and charged flows, weak effects can add up. Relativity itself offers an elegant cross-check. The deflection angle depends on how close the light path grazes the sunday. That geometry changes hour by hour as the comet rounds perihelion. A pure relativistic shift follows a known curve. A mixed shift that includes thrust rides that curve but refuses to match it. Fit the time series with a general relativity template and examine the leftovers. If the residuals cluster in phase with the rotation period, you have a smoking gun for jets. If they track the heating cycle with a lag, the engine is thermal. The instrument suite brings leverage. Millimeter observations can lock onto a specific molecule and measure its Doppler shift, which reveals bulk flow speeds in the coma. Fast, collimated gas suggests nozzle-like vents. Broad, slow outflow suggests diffuse sublimation. Ultraviolet lines from hydrogen reveal water breakdown and therefore water abundance, which ties the thrust budget to a tangible reservoir. Polarimetry can see whether the pushy phase coincides with a change in grain size, which would betray bursts of fresh dust. When several of these rise and fall together, the model space tightens. There is a geometric twist that can hide in the numbers. A small radial push near perihelion does more than move the object a little to the side. It can rotate the hyperbolic trajectory so that later encounters shift by large distances. On a retrograde track that skims the planetary plane, that rotation has extra leverage. This is why modest position residuals now matter for the choreography we saw earlier. A whisper at the point of greatest curvature can rearrange the entire downstream calendar. None of this requires exotic technology. It does require plumbing that is both strong and old. A crust sculpted by eons of radiation can hold pressure, feed narrow throats, and create jets with high exhaust speed. Pair that with a composition rich in carbon dioxide and carbon monoxide that wake early, and you have a recipe for thrust that peaks near the sun without a thick blizzard of gravel. If that is the truth, the missing cloud will not stay missing. Fine dust and gas will paint the path as geometry improves, and as the nucleus sheds the afterglow of its close brush. The opposite outcome is bolder, a residual that survives multi-wavelength astrometry, that refuses to phase with rotation, and that outruns the mass budget of any reasonable vent would force a new conversation. Before anyone runs there, the community will do what it always does: check calibrations, refit the lensing curve, reprocess the centroid maps. Only when the leftovers remain after that slow grind will the field accept a push without a pusher. The clock is short, and the instruments are ready. The planet is watching because the next window does more than test gravity. It sets the stage for how we design the decisive campaign that follows. The window after perihelion is not a pause. It is when the curtain lifts on the interior. As 3i Atlas climbs out of the glare, each day adds distance from the sun and separation from the field of scattered light. The geometry improves, the atmosphere steadies, and the instruments sharpen. This is when deeper layers begin to breathe. If the missing debris is real, it should sprawl along the path as a faint, pressure-sorted fan. If the sky stays too clean for the thrust we inferred, that absence will harden into evidence. Designing the hunt starts with cadence. Brightness and spectrum must be watched like a heartbeat. Night after night, hour by hour when possible, the curve should reveal whether activity relaxes onto a smooth slope or keeps flickering in short bursts tied to rotation. A smooth glide argues for a single dramatic event that is now cooling. A flicker pattern argues for plumbing that opens and closes with spin or stress. The difference sounds subtle. It decides which models get to survive. Wavelengths divide the labor. Optical spectrographs chase the fingerprints of molecules and small dust. Infrared instruments weigh heat and grain size when sunlight becomes warmth. Ultraviolet sensors look for hydrogen that betrays the breaking of water. Radio and millimeter arrays trace flows of carbon monoxide and carbon dioxide directly and can time their velocities with Doppler shifts to see whether the outflow is broad or jet-like. If the geometry is kind, radar adds the hard numbers: distance to the meter scale, speed to the millimeter per second scale, shape that hints at voids and caps and stubborn ridges where vents might anchor. Mapping polarization becomes a map of microphysics. Draw the trough across the coma and watch it move. If the deepest negative band rides with a jet, alignment and grain, birth conditions are steering the light. If the trough blankets the entire halo and refuses to swing with rotation, the grain population is globally strange. Repeat in several colors. A trough that fades toward longer wavelengths points to very small fragments. A trough that stays deep hints at layered, porous aggregates built by the radiation crust. Photometry is not glamorous, yet it keeps the campaign honest. A clean light curve across longitudes catches outbursts that a single observatory might miss. Behind a cloud or a sunrise, by handing off the object from one night side to another, the planet becomes a continuous watch. Amateurs carry a real share of that duty. A small telescope under a steady sky can mark a surge that triggers larger instruments to pivot. The data stream becomes a living map of when to point the sharpest eyes. Calibration and cross-checks are not chores. They are the backbone of trust. Instruments on different mountaintops see the same lines rise and fall. Space-based sensors with coronagraphs confirm that the background is not playing tricks. Teams trade, reference stars and standard lamps to keep scales aligned. When the curves from different sites overlay without coaxing, the story is strong. When they do not, the gaps themselves can hint at geometry or grain effects rather than at mistakes. The calendar adds pressure and focus. A near-Earth pass in mid-December delivers the loudest signal we will get. It is close enough that radar might bite, close enough that small telescopes can trace the halo into the dawn, and close enough that tiny astrometric shifts add up to a verdict on non-gravitational push. Schedules read like flight plans. Start with a nightly scaffold on medium telescopes. Layer high-resolution spectra from the largest mirrors during the darkest hours. Reserve radar windows if the angles line up. Keep a rolling task force ready to pounce on any sudden blue swing. Each channel carries a testable promise. If water truly is scarce, the ultraviolet hydrogen glow will be small compared with carbon species. If the thrust came from narrow vents, radio lines will show fast, collimated flows rather than a slow, spherical breeze. If the debris field exists at the required scale, deep imaging will catch the stretched, size-sorted fan that sunlight pressure sculpts. If polarization owes its abyss to exotic aggregates, the trough will keep its depth even as the viewing angle changes. The world can watch this unfold in real time. Public archives post spectra within days. Citizen observers upload frames before breakfast. Analysts push preliminary fits that anyone can check. There is no private corner for a result of this scale to hide in. The same transparency that feeds speculation also forces discipline. Claims that survive the echo chamber tend to be true enough to climb into journals. What happens over these weeks does more than settle a single argument. It tells us how to plan for the next visitor from another star. Do we need dedicated millimeter ears on permanent standby? Do we need a rapid response radar mode for hyperbolic intruders? Do we need polarization mappers that can swing to the sun at awkward angles? The answers depend on what 3i Atlas does as the clock runs. The test is public, global, and unforgiving. Either the sky reveals the aftermath that a massive jet demands, or it does not. Either the dust behaves like the product of a billion-year radiation kiln, or it refuses the mold. Either the centroid drift follows rotation and heat, or it walks away from both. When those cards land, the next question arrives with them. If the natural stories still carry the day, which one wins? If they do not, what threshold of evidence would justify asking for something bolder? That debate waits on the other side of the data. Two families of stories now share the same desk. One says nature did it under extreme but lawful conditions. The other says we might be watching an artifact of intent. Curiosity pushes both ways. Discipline pulls us back to tests. The only path forward is to write the bar for evidence in clear ink and hold every claim against it. The natural case begins with birthplace. A nursery salted by supernova ash could skew metals, lifting nickel against iron and leaving a chemical accent that survives for eons. Add a voyage across the galaxy under constant radiation, and a thick organic crust forms that reddens light, blocks heat, and forces gas to escape through narrow throats. Inside that shell, pockets of volatile molecules can pressurize and vent like geysers. Jets then deliver thrust with less gravel than intuition expects, which softens the missing cloud problem and dovetails with strong signals from carbon dioxide and carbon monoxide. This picture can also account for the anti-tail reported months earlier. With the right grain sizes and a jet geometry that points sunward, dust can briefly defy the textbook and paint a spike toward the star. The polarization trough slots into the same framework if the crust manufactures porous, layered aggregates that align as they leave. Laboratory work is nudging that way already, and if those curves finally match the depth of the trough, the dust puzzle bends toward a natural kiln running on cosmic rays. What the natural story still wrestles with is the stack. Retrograde motion near the planetary plane, flybys clustered by chance, the perihelion timed for maximal glare, a blue swing that seems to outpace a smooth thermal budget, position residuals that hint at a push without obvious fallout, and metals that read like a dialect no local comet speaks. Each piece can be argued. Together they keep the temperature high. The cure is not rhetoric. It is prediction that lands on a calendar and either hits or misses. Selection effects also deserve oxygen. Surveys are best at what they stare at, and they stare at the planetary plane. A path that crosses the ecliptic wins more often in the discovery game. The small number of interstellar visitors cuts both ways. Oumuamua carried a gentle non-gravitational drift without a coma, and left us arguing about thin sheets and thermal forces. Borisov looked comfortably, comet-like, and became the control case. 3I Atlas lands between those poles with chemistry that refuses to be average. With only 3 examples, pattern and accident sit almost on top of each other. Set the bar now. A natural model earns trust if several channels rise, and fall together in ways that match its plumbing and chemistry. Radio lines must show collimated, high-speed outflow when astrometry demands thrust. Ultraviolet hydrogen must either bloom with water or stay small if water is scarce. Polarization must keep its depth across viewing angles if the dust population is globally odd, or it must ride with specific jets if alignment is the driver. Energy budgets must close when you add sunlight and subtract heat and mass loss. The intentional story speaks softly because it knows the cost of speaking loudly. It asks whether a path that looks optimized, a surface that looks engineered by radiation shields, and a push that seems efficient could be signatures of survey hardware. It does not claim them. It sets tests with the same severity as the natural case. Radar should find geometry that departs from the chaotic shapes of rubble piles. Non-gravitational acceleration should decouple from rotation and day-night heating, repeating with a cadence that argues for active control. Emission lines should show narrow bands that make chemical sense for propellants and not for simple sublimation. There are cleaner falsifiers than confirmations. A broad, pressure-sorted debris fan at the required scale would crush the need for exotic steering. A laboratory match to the polarization trough using radiation-processed organics would remove the urge to invoke novel materials. A water halo large enough to anchor the thrust would shove the chemistry back toward the familiar. Each of these outcomes keeps the story extraordinary yet natural. The opposite outcomes would not end the debate by themselves. They would raise the bar for the next round. A stubborn absence of debris at the needed scale, a residual push that survives multi-wavelength, astrometry, and refuses to phase with spin or sunlight, a radar silhouette with unexpected uniformity or symmetry, and a metal balance that stays outside known stellar pedigrees, even after careful rechecks. Stack those results, and the field would be obligated to ask a harder question. Before the final push, the responsibility is to anchor curiosity to method. Write down the thresholds. Publish the templates for light curves and line ratios in advance. Share the polarimetry protocols and the centroid fitting code. Make it impossible for a bold claim to depend on a private calibration or a quiet assumption. When the data arrive, the outcome should be visible to anyone who cares to look. The debate is not a show trial. It is a rehearsal for the next visitor. If the natural stack wins, we will have learned how to read a surface sculpted by deep time and how to catch a clean jet without a dirty sky. If it does not, we will have written the first draft of standards for recognizing a messenger that is more than a comet. Either way, the terms are on the table and the clock is nearly out. Proof is not a feeling. It is a checklist that survives every attempt to break it. For this case, the first box is closure of the energy and mass budget. At the same distance from the sun, with the same surface that physics allows, the light curve and the gas production must add up without hidden loans. If thrust is real and large, then the reaction mass must appear somewhere in dust or in molecules with measured velocities that match the push. If that ledger balances, extraordinary claims are unnecessary. If it does not, the search for a missing term begins in earnest. The second box is astrometric honesty across colors and time. General relativity gives a curve for light deflection that depends only on geometry and mass. Solar radiation pressure gives a slower drift that depends on grain size and sunlight. Subtract both, and the leftover must either track rotation and heating like a jet engine under a moving lamp, or it must refuse those rhythms. A residual that repeats without caring about spin or day-night cycles is the kind of signal that forces new thinking. A residual that dances with vents and thermal lag is a lesson in plumbing, not a revolution. The third box is a fingerprint in polarization and spectrum that a laboratory can mimic. If porous aggregates made by radiation processing can be grown in chambers, bombarded, measured, and shown to reproduce the depth and shape of the negative trough, then the dust is strange but not mysterious. If no recipe can reach those depths without invoking layered microstructures that act like designed lattices, the field will take notice. The path to bold claims still runs through the bench. Show a material that does it, or show that nature cannot, and be prepared for what follows. The fourth box is geometry at the meter scale. Radar is blunt but decisive. A natural rubble pile wears seams and scars and uneven reflectivity. A silhouette with unexpected uniformity or symmetry would not settle the case on its own, yet it would narrow the options and set off a global sprint to reobserve before the window closes. Even a partial echo that pins rotation and surface roughness can kill or support entire classes of models. The hardest questions sometimes yield to the simplest tools. Send a chirp, time the return, measure the spin. Once those boxes are checked, the verdict should be visible to anyone who cares to look. If the debris fan appears at the size implied by the thrust, and if radio lines show fast collimated gas that rises and falls with rotation, the natural story stands. If ultraviolet hydrogen blooms to match water-driven jets, the chemistry tilts back toward the familiar. If polarization curves match a lab product made by long radiation runs, the dust puzzle falls into place. The claim, then, is not that the object is ordinary. The claim is that nature has more room than our habits admit. The opposite stack would not hand us certainty, but it would demand courage. A persistent push that outruns any realistic mass flow. A sky cleaner than the thrust budget allows. A radar shape with coherence, where chaos should rule. Metals that hold their off-normal balance after every calibration is redone. At that point, the community would be obligated to write down what signal would cross the final line. A repeating modulation inconsistent with passive venting. A narrow emission band that fits a propellant channel better than a sublimation line. A trajectory change that arrives on a cadence no thermal map can produce. Set those thresholds now, before the noise of headlines arrives. Whatever the outcome, the next steps are already clear. Build a rapid response chain for interstellar visitors that treats hours as gold. Keep a millimeter ear always listening near the sun so that carbon monoxide and carbon dioxide lines are never missed again. Upgrade coronagraph pipelines to push deeper into the wings of bright events. Equip a handful of medium telescopes with fast polarimetry so that the next trough can be mapped before it fades. Most of all, design a small intercept craft that can wait in a parking orbit and sprint when an alert pings. A single flyby with a spectrometer and a dust analyzer would answer questions that a planet full of telescopes can only circle. There is a cultural legacy here as well. Open data is not a slogan. It is the reason these tests can be trusted. Post spectra quickly. Share reduction code. Publish the templates for fits before the results land. Invite amateurs into the timing network so that no surge slips past a cloud or a sunrise. The cost is noise and hot takes. The reward is resilience. Claims that can be checked are claims that matter. If the ledger closes on a natural engine, the lesson is not smaller wonder. It is deeper wonder. A crust carved by billions of years of radiation becomes a kiln that manufactures dust we have never seen, and plumbing that turns gas into clean thrust. If the ledger refuses to close, we enter a slower season that will test our patience and our philosophy. Caution is not cowardice. Evidence is not the enemy of imagination. The way to be worthy of an extraordinary answer is to keep asking ordinary questions with ruthless care. The visitor will fade, the data will not. Students who watch this campaign will write the proposals for the next one. Engineers who sketched an interceptor on a napkin will draft a mission plan. Whatever the final label, 3i Atlas has already widened the map. Proof is a destination, but the road is the point. We measure, we argue, we learn. The sky does not owe us neat endings. It offers chances to earn them.